will it just work, or what are the technical barriers to using anything other than lithium? What is stopping us from producing a working sodium battery?
The problem is that sodium is much larger than lithium. The atom is just much larger, so it does not work with the same materials we are using.
So maybe this next statement is coming from a bit of ignorance, but if it is larger, so wouldn't that be a volume issue and not a actual chemistry issue?
Yes,
it should
exactly.
still produce the correct voltage, but it will just be a bigger battery to produce. So is that the case, or
partly yes, but you don't have enough space. So sodium batteries, as you say, you can use sodium. That is also being done as discussed, but they have so much less energy that it's really tough to compete with lithium. And secondly, you cannot use the same raw materials. For graphite, for example, as I said, lithium goes in these graphene layers, and sodium is too big to go inside. So you need to tweak your materials that it actually can store sodium. It is possible, it's solved the problem, but it's not just swapping. And that's why, because of these properties, lithium is just number one. But it's possible. You also read about potassium batteries or iron oxide batteries and so on. There are many different research studies, but nothing is beating lithium. So lithium systems, just very quickly, you can either go with metallic lithium. These are actually solutions also existing. Without any carbon or storage capacity, or you can use systems without metallic lithium. That is in use today, as you see, with liquid electrolyte, and you only have a little bit of lithium as ion in it. But as I said, the solid-state batteries, some of them use metallic lithium, and that allows you to increase your lithium content by a lot. That's also why energy density is growing, but lithium has a very big problem that is super reactive. So it reacts with water and with air. And if lithium metal touches water or air, it immediately gets very hot and reacts to lithium oxide. So there is also an issue, but there are also already for several years battery cells available, and research is very strong. Yes.
So lithium in its amalgamated state with graphene will still react in a similar volatile fashion, or is it something once it is part of the graphene ring?
Once it's part of the graphene, it's not metallic. It's stored as lithium ion, not as metal. So that's different.
So the chemical risks involved in lithium are mitigated because of this?
Yes, and that's why this is actually also the main solution, because the risks are much lower. So how it works, who doesn't know how lithium batteries work, or everybody is more or less familiar? Yeah. Yes, so if it's too slow, just let me know, I can also speed up. Yeah. It's called rocking chair principle because, as you said, the lithium actually is not undergoing any chemical reaction here. It is only losing one electron, and that makes it from lithium metal to lithium ion. That's why it's called lithium ion battery. But this ion, actually, it doesn't form any new chemical or whatever. It is just stored in between here, graphene layers on the right, as lithium plus. Nothing more is happening, and the other way around. It is stored as, it is actually integrated into the crystal structure of this, here is NMC, this is how NMC looks like. And there it is recombined, but always as lithium ion. And the electron that it loses, it goes then actually over our electrical circuit, because here we have a separator for electrical isolation. The electron, it must move outside of the battery cell over the load we want to have, and then it can actually recombine. So the electron has minus load and the lithium plus has plus load. And it's called rocking chair because the lithium plus really is just going back and forth and nothing more is happening. So more or less quite simple. As I said, this is graphite. It's not graphene in itself, it has so graphene in itself has a lot of research with it, but this is graphite, but graphite consists out of graphene layers. So just another depiction is the same principle. Here we have the negative electrode, the positive electrode, some materials that are used for it. As I said, most dominant is currently graphite on the negative electrode or the anode. We have the trend for graphite and silicon, and what you also have is this. It's called lithium titanate. So that is titanium oxide, and the lithium can also be used. Can also be stored in that. We will come to it a little bit later, but the so-called LTO batteries, they have very, very, very high power density compared to all of the other types of batteries. On the cathode side, positive electrode, as I said, we have our 3 metal oxide, combined also called NMC, or we have the chemical formula is this is cobalt oxide mixed with aluminum, it's called NCA. It's predominantly used by Tesla, that's why it has a big market. Or here, NMC in any mix that you can imagine is also played. The separator you see usually is very common. Separator material is polyethylene or propylene, so it's very common. Of course, when we talk about solid-state batteries, we also talk about switching this separator to a ceramic separator in order to be that it is more mechanical stable. Or polymer kind of separator that is used in fuel cells is also investigated and so on. But state of the art is only this full PE, PP separator and liquid electrolyte. Okay, some words on electrode voltages, because that is actually determining your operating window of your battery cell. You always have a negative potential and a positive potential, so it's a little bit confusing probably. Whenever you talk about half cells in electrochemistry, you talk about potential. So that's the potential of this half cell versus some reference point. And always when you have a delta potential, so when you have 2 potentials that you subtract, you talk about the voltage. That's why that's a different term, it's just the correct scientific term, let's say. So looking at a battery that is made out of carbon and metal oxide, so cobalt oxide, nickel oxide, manganese oxide, whatever. Usually the negative electrode, so graphite, they operate at a potential versus lithium of just about 0 volt and a little bit above 0 to maybe 0.5 absolute maximum. And the positive potential goes, as we know, for most battery cells, usually up to 4.2 volts. It is limited here. Does anybody know why it's limited to a certain upper voltage range? It's because the electrolyte is not stable at higher voltages. So it's not because of the material. This material cannot withstand it. It's usually always limited because of the electrolyte.
So this is true for lithium cells or any cell in general?
What is true?
Electrolyte is unstable at higher voltages because
Yes,
most cells
always true. Yes,
for any cell.
yes, for sure. Especially for liquid electrolyte.
So lead acid as well.
Especially lead acid, yes. So one thing to remember, whenever you have an electrolyte based on water, the voltage limit of water is 1.23 volt everywhere. So whenever you have water involved in any form of battery, your cell voltage is always limited to 1.2. Or even a little bit below, but the official limit is 123. So 1.23 volts for water. It's actually quite nice to remember. For lead acid, for example, it is also 1.23 volts. And that's why in your automotive lead acid battery, you have always 6 battery cells in series to come to our 9 to 16 volt, whatever you want to have. Yes. Above, what happens above 4.2 is said electrolyte decomposition, and that usually leads to a thermal runaway. And below 0 volt, what happens? That it is electrochemically, it is more favorable to produce lithium metal instead of lithium ions. So this you can remember, whenever your lower potential drops below 0, you will always destroy your battery cell. And it is important for many applications there. We will talk about it several more times today. So it's called lithium plating, and yeah.
So the lithium plating process, is this a reversible process or is this?
No, it's not reversible. Usually not. Yeah, there's research ongoing, but I would say if you cause plating in one of your experiments, you would probably throw away the cell.
That's right.
Yes. So remember, plating occurs at negative electrode potentials below 0. That is not the cell voltage. That's important to remember, but negative electrode potential below 0. Okay, looking at LFP. So LFP actually has a lower stability window, meaning that we can also usually charge it at 3.6. I have also seen 3.65 usually is the charge limit of LFP battery cells. And because the negative electrode is also graphite, it's still the same lower voltage limit. But LFP batteries have a major advantage. If you overcharge them, they don't have a thermal runaway. They can, important to understand. Thermal runaway means you have a self-ignition of the battery. So if it gets too hot, if you have a battery with this metal oxide and it gets too hot, that means the temperature will rise by itself. So you can throw it in cold water and probably it will still begin to burn. That is what is called thermal runaway. So it means if you heat an LFP battery to 100 or 200 degrees, it will also burn. Yeah, but it will not start to burn by itself. That's what I mean.
So according to this, when we overvolt the LFP, so is it completely safe for the battery itself, or will we still degrade it?
Absolutely not. You will still degrade it, but it is not, you will probably not cause a huge fire. Yes, but still, please don't overcharge the battery cell. Never.
I've seen enough videos to do.
Yes.
One more thing, I don't understand the correct situation where we will have a negative anode voltage, the situation where we will see lithium plating. So how can
we will come to it a little bit later. So the voltage will never be negative, but the anode potential can become negative. Then you have something called LTO batteries. Maybe a topic to remember, if you talk about LTO batteries, the negative electrode is switched. So this time it is not the positive electrode that is changed around and so on, but you have titanate oxide on the negative electrode, and here you still have your NMC or whatever material. So the upper voltage remains similar, and the lower voltage is increased. The LTO has a potential around 1.5 volts. That means we have a thermal runaway risk, but we have no plating risk. So that is why LTO batteries are really nice for low temperature power. They can provide much higher power at 0 degrees, for example, compared to LFP or NMC cells. And yeah, you could in theory do an LTO LFP battery cell that is safe for in high voltage regions and safe for low voltage regions. But you really have a very small usable voltage window, and that's why it's not an application. It would be safe, but the energy content of such a battery cell will be very, very small. And I think it's not available on the market, unfortunately. Okay, this graph is quite, yes? Sorry?
How does lower and upper voltage?
Yes.
How is that? It is based on the property they have defined the 4.2 up to 4.2.
Yes. That's based on the materials you use only on the electric. material. So this is not the cell voltage here that you see here. Okay? No? We can discuss later. So when you look about designing a battery cell, you have an anode, negative electrode, and a cathode. And as you know, they have graphite or some other material, and NMC or some other material where the lithium inside is stored. And now, ideally, what you want to have is that, let's say, 1 gram of carbon can store the exact same amount of lithium than 1 gram of NMC. But it is not the case. So they have two materials on the anode and cathode you're using. They have two different capacities for lithium. And that's why when you are designing or building a battery cell, you need to actually do a balancing of your anode and cathode. So you need to match the size and the mass of the material you are using so that the battery works. A little bit of background knowledge is important for some effects you can measure on the cell. This is the background to it. So what you see on the bottom is state of charge of your full battery. And what you see on the y-axis is the cell voltage of the battery cell, really. And the two graphs is the open circuit potential or open circuit voltage that you can measure of the single electrodes. So this is not of the full cell, but of the single electrode. And you see, as we mentioned before, the graphite looks like this. It is always near zero and approaching zero when you go up to higher states of charge. And the NMC, the curve looks like this. And what you have in total, you subtract these two. That's what is done. You subtract the red line from the blue line, and what you get is the green line. That is actually the OCD you measure on the battery cell. If you take it to the lab and you want to measure the open circuit potential, it is always the delta of the two electrodes. You will not be able, this is a lab experiment with self-built cells to get these curves. They are usually not available, but just to understand where it's coming from. And what I just wrote here is usually you use the battery cell, the SOC of course, from 0 to 100%, and that usually means you go somewhere from 1.92 volts to 4.2 volts or something. And what it means on a material level for the graphite, it means you go from 1.4 to 88.4% of material use. So in theory, you could use even more. You could even store more lithium in the graphite. And for the NMC, it is even more drastic. The NMC could, in theory, store much more graphite. So you see, you use only from 96.15 to roughly 43% of the NMC's capacity for lithium. And why is that? You only do that because you run into your voltage limit, as we said before. So you are not allowed to go below zero because this will destroy the battery cell due to formation of lithium metal or plating. And if you go above 4.2, 4.25 or whatever, you run the risk of decomposition of your electrolyte and NMC turnaround. So that's why it is limited, and that is why the two electrodes usually have to be designed. And this have to be designed, it actually means that the size of the electrodes and the thickness of the layer of the electrode is different for both sides. I mean, it makes sense, anode and cathode, they have a different thickness and they have a different weight. So that means that you have a different amount of active material. But this is the reason that you need to balance the lithium storing capability. So, yeah, just to be clear, this is over-dimensioning of the anode. That is, of course, not good for efficiency, but you must do it for this system. In the beginning, usually you also lose a little bit due to formation. could in theory handle 56.74 amperes. So yeah, as with everything, cell is always limited by its weakest link. So the cell capacity would be something around just above 30, although the cathode would be capable of doing more. Sticking with open circuit voltages, so the one of NMC, it looks like this, we have just seen it, coming from 4.2 something to just below 3, usually it's 2.6, but the cells usually are often used not to the lowest voltage point. However, what I want to show, LFP, which is the second most popular battery material, the open circuit voltage looks like this. So from battery cell capacity 0 to 100%, you have almost no voltage change, at least in a certain region, maybe up to 80%. There's almost no voltage change, and that is one, let's say for a BMS algorithm, this characteristic is really challenging. But it is not clear, or it can be done, but it is complicated to estimate the state of charge. Because usually for the NMC, you can see it is, what you do is you measure the voltage, you are at 4 volts, okay, I am 10% SOC, and that's what you can display to the driver or on the smartphone to the user. You are at, I don't know, 3.35 volts, and you know exactly, okay, I'm charged 89%. Whatever. So this is the simple state of charge algorithm, and for LFP you have to be a little bit more complex. So you need to usually measure the current, do amp-hour counting, or you use Kalman filtering and so on. So there are many publications, many papers, and many methods to do it, but it is complicated, more complicated than for other chemistries. Just for your info, LFP usually is the only material that is complicated. LTO is also not so easy, but it is hardly used. And the rest of the materials, just for your reference, they all behave more or less similarly. So there was, let's say, more or less a little bit introduction, electrochemistry. Now I have very electrochemistry focused slides. So if that's too much for you, if you didn't have it in your studies, just raise your hand if it's not understandable. I try to explain. Whenever you are studying electrochemistry, usually you always look at interfaces. So for example, when your anode is touching the electrolyte where the lithium is in, there's an interface somewhere where you go from solid to liquid. And in electrochemistry, you always study exactly this interface. I just wanted to show it here. And there's always a moment when your lithium, or whatever you have, it needs to go from liquid into solid, or it needs to pass from solid to liquid, or it needs to move from lithium to lithium plus, for example. There's somehow, somewhere, there is a boundary where this happens, physically. And this you can calculate, and this is where many of the characteristics of the battery cell also come from. So I described like this. At the boundary layer, you have always, or almost always, something called the double layer. And what it means, double layer, it means that you have on the left side here, for example, in the electrode, in the graphite, you have a layer where your charge distribution, so of your charge carriers, electrons, is depleted, and in the liquid you have the same. Assuming, for example, our lithium comes from here to the electrolyte and approaches the electrode, of course, because here is a plus charge, positive charge, it will attract out of the electrode an electron, a negative charge, because it is just the natural phenomenon that the charges, they want to compensate each other. And so you will always have, when you hear lithium plus, you will have a layer here where you have an excess, you have more electrons than in the rest of the material. That's basically what electrochemistry describes with formulas. You see here is the reaction, so lithium or any other metal, you have it as an ion, and if you combine it with an electron, again, you have metal. basically what's written here. It's not super complicated, but it also happens physically. So there's actually an electron moving to meet the metal. Okay, what happens when this happens when you want to charge or discharge your battery cell? You introduce overvoltages. And overvoltage is a term of electrochemistry. It basically means the ohmic voltage drop is one category of overvoltage. So you have a voltage drop because of Ohm's law, and there are other laws with other voltage drops basically. These are listed here. So you have something that is called charge transfer. That is one of the main characteristics also for modeling of lithium-ion batteries. If you are into that or look into it, you will probably find the charge transfer part that is modeling the charge transfer. Basically, it describes when the ion and the electron here, they transfer. Yeah. If it's meeting or actually physically transferring is not so important what I described. Then you have something that is called diffusion overvoltage. It is this type of overvoltage is produced because for the lithium or any other metal to come to this double layer here, it needs to come somewhere from the bulk material. And that for the lithium to have a diffusion directly here, that takes time. And that is called diffusion overvoltage. And actually, that the lithium can travel to the double layer is one of the main contributors for the internal resistance of the battery cell, for example. Just please understand, this sounds maybe a little bit complex, but it's directly responsible for the characteristics of the cell that you can measure.
Sure.
Yeah.
I don't understand why, if lithium takes time to diffuse, why would that result in an overvoltage for the cell? Because if lithium is the main ingredient that is creating the potential difference, if lithium is infusing, that should maybe create an undervoltage.
It is creating an overvoltage because it takes time to diffuse there, to go there.
But
Yeah.
lithium is the one producing material that is producing the voltage. So if it's taking time to diffuse, we should have a deficiency of voltage.
Yes, we have. It is called overvoltage, but it's reducing your voltage.
Okay.
There will be a picture later, and then you understand it. It's not increasing your voltage, yes.
So one more question, so what will be the difference between this and an undervoltage situation?
Overvoltage here is a term. It's not what is meant is not that your voltage is increasing or too high.
Okay.
It just means these on the right side, these are effects that are responsible for a voltage change.
Oh, okay. So it will bump the voltage up.
It will not pump the voltage up. There will be a graph later. I think then you understand it. Yes, then you have resistance losses, yes, that everybody knows, Ohm's law. And you have something called equilibrium voltage. It is not equal to the open circuit voltage, please be clear, but it is always almost the same. Yeah, so you can compare it, but scientifically it is not the same. It's dependent on how much lithium you have actually in your electrolyte and how much active mass and so on you are using. This is not super important. And the voltage that you measure on your electrode, so if you take a multimeter and want to measure the voltage of your battery cell, it is always the sum of all of these overvoltages. Yeah. So, just as a depiction, this is what I meant. I think this should be more clear. When you have a battery cell, you measure voltage at 0 amps, you don't discharge it. You measure a certain voltage, and the second or the nanosecond you apply a current, you first have a voltage drop. That's because of the ohmic resistance. It's a linear voltage drop, just going down without any discharging of the battery. Yeah, so this is Ohm's law, this everybody knows, but similarly to ohmic voltage drop, you have, as I said, the other voltage drops as well. It but as I said, it is just describing how the voltage behaves when you discharge the battery. Usually that is the one that happens next. So it's like a curve, and you can imagine that it's really related to diffusion. So in the beginning, when you begin discharging everything, the lithium ions and so on, they are settled and they are equally distributed. And the second you begin discharging, you introduce something that is not in equilibrium. Sorry, I don't know the English word. So it's unbalanced. And the second that it's unbalanced, you will have diffusion from the species to get balance again. And that's where this curve, basically, that you always measure with the lithium batteries is coming from. So, as I said, anybody of you already heard Butler-Vollmer equation? Yeah, so if you ever looked into simulation of batteries, this is one major term. Yeah, so kinetics on the electrode are dominated by the Butler-Vollmer behavior. And that looks like this curve you can actually measure. So you see here delta potential, you can see that as voltage, and here you have the current. So it's only, quote unquote, only the relation of the voltage to the applied current on your system, on your battery cell. And that is based on the diffusion. Of course, on the anode and on the cathode, the reactions have to take place at the same rate. So if you take one lithium ion from the anode at the same time at the cathode, the lithium ion must be stored. So you can, a charge imbalance is not allowed because of the physics laws. This is always in equilibrium, and that's why this curve is there. Okay, yeah, overvoltage current. This is the equation that belongs to it. It's very famous, actually. It's, I think, the only equation I'm giving. But as I said, whenever you're looking into electrochemical model of batteries, this one you will find immediately. And called Butler-Vollmer equation. What you see here is you represent the anode and the cathode reactions for oxidation and reduction. The current is what you want to calculate, and you have the different components towards the voltage that we discussed before. So you have the equilibrium voltage, or what you often use is the open circuit voltage, the electrode potential, and then you have the temperature dependent term. So alpha is a constant that is for the reaction speed, and these are the normal physical constants of Faraday constant, temperature, and I forgot the name, sorry, it's also physical constant and temperature. Which one? No, I think not Boltzmann, no. I will look it up later. Boltzmann is called K usually. What you do, so you want, this is quite important because the voltage is also dominated by this. What you usually do is say, first thing you do is, the equations way too complicated. I'm not doing that. So usually what is established called small signal behavior. And that is when you only look in the small area here, you can say this is linear. So let's change our equation a little bit and make it linear. So usually what you do is the slope here that is linear, you can interpret it as a resistance, and it's called charge transfer resistance, and this is the equation for it. As long as you are in a small signal behavior. You can do the same for very large currents and overvoltages.